Okay, anyway, getting to time evolution, just like translation moves something over in position, this moves something over in time. Hamiltonian, I'm not, well, again, this is, you can figure out the time evolution operator based on the time-dependent Schrodinger equation, and you've seen how that was derived, not that everyone's 100% sure how Schrodinger did it. Okay, this is all fine and good, but recall that when you had a time-dependent Hamiltonian, that could get nasty. We haven't dealt with one yet. Hamiltonians have been relatively simple. P squared over 2m plus x squared, right? So you saw that. That's for a bond. That's not time dependent. So a time dependent one, which we'll do later on, has like cosine frequency times time. So then maybe that's light. Okay, so you haven't seen one yet, but they do exist. Oh, I should have little dots here. Little dots. Anyway. So a bunch of Hamiltonians. Okay, so because of that, it's not so straightforward to advance from t0 to some later time t versus t0 to t0 plus dt. And so we derive this. Well, it doesn't look so bad right now, but it's actually kind of hideous, right? So a sum of terms, each one with more and more integrals. And again, there's so many of these, so what you're really doing here is you're discretizing time into really dt, till they're infinitely small. So anyway, we talked a little bit about that. I mentioned no one, I rarely see this. So this is called a Dyson series. Again, I have almost never seen, I've seen it like once in a professional talk. And if you have a time-independent Hamiltonian, then you get this, which is what you pretty much universally see. Notice that because time evolution is unitary, the transpose is defined by this times what equals 1, and so it ends up being a complex conjugate. Again, I can't emphasize that that's just kind of dumb luck that it just happened to be a complex conjugate. The last bit, one thing you need to start thinking about is, what do you really do with this? So let's say that you want to involve some kind of ground state of a molecule. And we're using this more complicated form because it's time-dependent Hamiltonian. So what you're doing is you're shooting light on it. And what do you measure afterward? Now that would be what you project. So a sensible thing would be to project onto the ground state itself. So start with the ground state, shoot a laser at it, and then see whether it's still in the ground state later on. And this I would call a ground state leach. If you read time-resolved studies, so right now we're just down to Glusac is our laser person. It's unusual we only have one laser person. But any her group's papers are going to talk about ground state leach. So what you have is you have delta absorption over absorption. This is typically how this appears. And of course it'd be 0. This would be time in something like femtoseconds. And at 0, a pump hits a molecule, and it recovers. So you'd have a negative. So this would be a negative number because the ground state has been destroyed. So this ends up as, this operator will just put a 0 in front of it. And ground state overlapping ground state times 0 means it's no longer absorbing, so you have a negative delta A. So anyway, this is just one way to think about this. Okay, so now we got to get into more stuff. And as I mentioned, you'll never see this again. You're going to see this all the time. And I I happen to use this thing. I use this thing even when my Hamiltonian is time dependent because I'm lazy. I really don't even know how to deal with this. I've never tried. It looks awful, so I'm not even going to do that. I mentioned to you that you can minimize the error from the use of this thing by using the smallest, making t as close to t naught as you can. And then what I do is I use it over and over and over again to advance it to a longer time. And that minimizes error. Okay, so now what do we do with this? I just talked a little bit, so I'm getting you calibrated about how to think about using it. Using it is oddly a little more you think like, oh, okay, well, we're done with this now. Not really even close. We're just really at the beginning. Okay, one thing we can do is evolve states over time, and then we can make measurements and see how the measurements change over time, just like I was talking about. And what I want to do is, okay, we have a measurement, and we'll operate on its eigenstate. Okay, so you may recall that you were learning this about a month ago, and maybe your mind was blown, but now you're like, what am I even writing this down? Now this will be a dual ket. So you remember what that means, which if you don't, this is what it means. It's capable of spitting out two eigenvalues. It is the state is the ket of two operators. And don't forget, okay, here's some basic direct notation, which you better know for your exam. How do you turn operators into matrix form, right? Did you forget that? I actually forget it almost every year until I teach the class again. Okay, so to turn time evolution so again, the book kind of goes out of its way to write delta t as t minus t naught. It's really kind of annoying. You can either insert delta t or you can just say t naught is 0. So, the book likes to make things really exact and very wordy. It's actually kind of fine. And later it'll actually simplify this. So I hopefully notice that. So as usual, it's two resolutions of the identity, and we'll have an index. I'm using the book's notation. Instead of a dash and a double dash, it used m and n. They're not very consistent with this. That guy died a long time ago. He had cancer. So the problem there is that there's no updates. I don't think it's, they really need to go through the book and fix all those dashes and double dashes and do something just more coherent. It's just a little all over the place. It's kind of annoying. Okay, right, so that is the matrix form. Remember that what you see, I'm tilted, it bothers me, I can't look like that. There we go. So you have to stand back a bit. Nice and straight. The world will not explode. Okay, so remember that your matrix representation is really right there, in case you forgot it. It's been a little while since we looked at some of that. Okay, so we have a function of an operator, which then just returns the function of the eigenvalue. Again, I hope you remember that. Let's see, what do we got? Still got the sums. And I won't remind you what they are. A to the n. Now what's going to happen is, this is the operator, not the unitary operator, so I'm going to operate on the ket. Remember, you actually have to jump through some hoops to operate on a bra. You have to turn it into a transpose, and you have to flip some things. Anyway, don't need to do that. So it's going to operate on that particular one. And then this is e to a number, and e to a number is a number, so I can just factor that. I don't see any reason not to factor it out. And how did I put this matrices. Okay, so you can see why that's, again, you can see why I was a little annoyed about this notation. That's kind of hideous. I don't really have a choice about that. Now, again, of course, we're going to assume that this is a Kronecker delta. So that kills off one of your sums, and what you end up with is, and I will kill off the M, and mostly just because I have these N's here, so I'll just leave those. And I box myself in a little bit. So remember that, oops, oh, that's no good. So N's become N, nothing magic about that. Remember that M and N overlap, and only when M is equal to N do you not get to 0. So that's why M is magically turned to N's everywhere. Okay, now the trick here is that the matrix is diagonal. Now, they've stated a zillion times in any professional talk, when something is said to be diagonal, that has profound implications. It actually kind of means nothing is happening, really. Yes, that's in a very big picture. It means that, well, I mean, you know, at the very outset, of course, there's no diagonal elements. Okay, so the matrix is easy. But the other implications about that would be that states are not mixing with other states. And in this case, since this is the time evolution operator, what it says to me is that states do not mix with other states over time. So remember, take like SX. The SX operator will take an SZ state and turn it into an SZ plus, and will turn it into an SZ minus. If this was the SX operator, SX has off-diagonal elements. And what that means is it turns an up into a down in the Z representation. So it mixes states. It mixes states because it has off-diagonal parts in the matrix. The matrix is not identical, right? So things are turning into other things. That's what that means. So you have uncertainty principle. You have an uncertainty principle in play. You see, there's all kinds of implications about having an off-diagonal matrix. So when it comes to diagonal matrix, I get a little flummoxed because there's kind of like nothing to say. That's why I'm saying like not much is happening. States are not, this operator does not mix states with other states over time. So again, that's actually why I said nothing much is really happening. So a state will stay, if you have a state, let's say ground state, it will stay the ground state. The Hamiltonian is not going to nudge it off into an excited state, or it's not going to allow an excited state to kind of pick up ground state character over time. Let me make what I just said more explicit. And so again, to understand what the implications of this are, it's terribly important, but maybe it'd help if I start writing things down. So when it comes to why are we doing any of this, everything needs, I need to be able to understand measurements. Measurements use instruments. Instruments are represented by operators. So I need an operator. But an operator by itself is just, maybe it's a derivative, right? That doesn't do anything. So I need to have an operator and then a inner product. Okay, so, and what I want to do, of course, is, we've covered all this. So now what I need to do is talk about a state evolving in time. And again, I'll go back to my generic alpha. It's at time 0. So I'm going to time evolve it. And so that looks like this. Again, this is a little overly verbose. T minus T naught is kind of annoying. Oops. Let's see. Okay. Now, how do we deal with this? If I'm still going to be, I want to use a basis, right? Plus minus in first spin. Okay, so what I'll do is I am going to sum in. I'm going to resolve an identity. I'm going to try to figure out where to put it. It's always a bit of a, I'll use the letter N, like, so many times that damn thing uses a dash. Well, a dash, now all of a sudden the book decided to use A, B, N, which one minus. Okay. All right, now you see, again, the Hamiltonian is okay with dash and now I'm really perturbed with this little change in notation. The book suddenly goes from dashes and double dashes to N's and M's. It's a little stupid, but that's why I keep emphasizing don't worry about how it makes these little place markers. Okay, so what does this turn into? Again, a function of an operator. It's just the eigenvalue, function of that eigenvalue. Now let me. This is a number, right? It's an inner product, so it's a number, and so I'm evolving the ket. I'm just a big picture, right? So I'm having this state. I'm trying to evolve it, but of course I'm using this representation. So this state is a sum of maybe spin up and spin down. And of course that's our old friendly coefficient. For a state that happens to be Sx plus, this would be plus 1/2 spin up, plus 1 over square root of 2 spin up. And then there is a plus 1 over square root of 2 spin minus. All right, but notice now that instead of just a coefficient of a to the n, it is now, and so I used to write this like this, a coefficient for the a to the n state that represents alpha, but now it's time dependent. For all of this jazz, the coefficients as you've done them, but now you're picking up a thing that has time in it. And now, of course, this is now the time evolving alpha state. Okay, now big picture here, this is kind of a big one. But unfortunately I have to tell you, it's actually rarely useful, but it's so simple. We almost always represent a state in some kind of basis. So all you do is slap on e to the minus I energy t over h bar. Just multiply by e to the minus I energy t over h bar. And now it's a time evolved state. So we knew how to represent Sx before, right? The Sx plus state is just 1 over square root of 2 plus 1 over square root of 2 minus. Just giving that example. Now just multiply each one times e to the minus energy of that plus state, plus 1 over square root of 2, e to the minus energy of the minus state, minus. It's unbelievably easy, right? There's nothing to it. It's deeply trivial. And cool, problem is rarely useful. What we tend to find is that you rarely run into problems that allow such an easy solution. Now, in terms of what can I mean? I mean, this seems like this is how we did everything, right? I mean, yeah, we always expanded, we always resolved identity, so this little character is new, it's rather trivial, in all honesty. But we always had a state and we always resolved identities. What else is there? Okay, let me point out, I got one more thing to do with this. Let me point out is that I was using an eigenstate of the Hamiltonian. What if I don't? Okay, heads up. Heads up, this gets way more complicated because of basically what I just said. All right, before I get there, let's use this for the simple cases that, again, almost never matter. But these are baby steps, right? So in terms of understanding time evolution, this is like at the beginning of class when I'm telling you about free waves, which are actually useless because they don't actually describe anything. Okay, so now again, and I'll be more careful about my notation. Both uses dashes here. Now we assume that A and H commute. So, as you can imagine, that might be important. Actually, I shouldn't have erased all that stuff and writing the same damn thing again. It's just not complaining on my part. Okay, so again, simplest case possible. Now that we know how to evolve the states, let's use the evolved states left and right of the operator. And that means that now I'm time evolving the expectation value. Okay, so what does that mean? Alpha, T0, T. So there's your time evolution. A is still A. Cat to the right, bra to the left. Okay. That's the transpose, because that's how you evolve the bra. Fortunately, we know what it is. And sorry, just screwed that up. And what I'm going to do here is assume alpha. Sorry, I needed to mention this too. Yeah, so this is kind of important. Okay, so this is a pure state. Okay. Now, the reason that you can tell this is a pure state is that I didn't sum this times a coefficient, right? So here I did this here, so I showed you how in general how to time evolve the state, but I'm assuming that all the coefficients except 1 are 0. Now, the big picture here is, again, here's how you time evolve a ket. And bras, of course, are just complex conjugates. And now I'm calculating expectation values, which are the end result. That's why we're doing all this. But I'm going to do it in small steps. I'm going to show you cases like in this case, here's what you get. Now, the reason is that, again, this is going to turn out to be stupid simple. I got another one that'll be stupid simple. And then I got one that's going to, it's mathematically not too bad, but it's actually going to conceptually blow your head off. Okay, so now what does this turn into? So as I mentioned, this is actually going to be really, really, really easy. Now again, I'm not saying it's a sum of a to the n, it's just a to the n. Maybe a to 1, right? It should have done it that way. Okay, since this is the transpose, there's a plus. Okay, so what I did was I had the transpose act on the state. Now this is the regular time evolving operator. So there's a minus. Now what? What do you think happens now? Yeah. Very important concept.
It's like AI operator.
Yeah, well, these are numbers. Either the plus one, either the minus one. What?
Just get one.
See that? No time evolution. Time disappeared. So whatever, okay. What is the SZ polarization for the plus state? Given that the Hamiltonian, like it's in a magnetic field in the Z state, so Z up, Z down, or good energy, bad energy. What happens? Nothing. Right? So again, you've got to be careful of my conditionals. Operator, okay, it's SZ. And I'm operating on a pure state, so that would be plus. So SZ plus is h bar over 2 plus. Okay, so again, the easiest thing possible. The Hamiltonian, now this would have to be something that affects plus versus minus energy. So it has to be a magnetic field, it has to be aligned in the Z direction. So one of these, the plus state is good energy and the minus state is bad energy. So in other words, it's about as simple as I can make it. The end result is that nothing happens. If you measure, so if I'm measuring SZ on the plus state, the answer is h bar over 2. It's plus polarized. That's what I measure. Later, I measure the same thing. And if I wait more, I measure the same thing. Nothing changes. So now, again, I've used very generic notation because that's how I have to do it. But I hope my polarization example kind of makes sense. I mean, if you can, I know it's kind of subject to say equations, but anyway, it's the best I can do. Okay, now let's ask ourselves, what about the SX polarized? Sorry, we're in the plus state, but I'm going to ask SX. What is the SX value? What's the polarization in the X direction? And I don't really care what it is. I wanted to see whether a T is going to get canceled out or not. Right? So I'm really, I don't actually think that case, I think that would be 0. The operator is actually 0, but I don't really, that's irrelevant. I want to know what the time evolution is. I mean, you folks should be able to you know that's 0, right? The reason is that SX has no off, is only off diagonal, right? And I'm asking what's the diagonal position for 0. So anyway, so you know that. I don't care about this. I want to see if this changes over time. That's my end goal. Now, let me throw out the conditionals in this case. So in here, I'm going to ask about, I'm asking a question using a basis that it doesn't commute with. Now again, that would be, I'm going to use SZ plus and minus, but I'm going to ask SX over time, right? X, Z, minus SY, something. Anyway. Okay, so what do you get? What's this? Okay, so let's take alpha T naught T theta alpha. Okay, now again, alpha T naught is going to be pure state. Again, it's not written as a sum. Okay, so what do I get? I get the n. Here's my evolution of the bra. Here's my operator. Here is me evolving the cat. And you know what you're going to get? You saw me screw up there. That was a good save, wasn't it? Right, you can already see what's going to happen, right?
Time disappears again.
Yeah, it's going to disappear again. And again, no time evolution. So, asking, I know, remember a big picture, don't forget this. If you're asking what is the, what is the X polarization of your magnetic moment for an electron that's pointed up, you get h bar over 2, but out comes the spin down state, right? So remember, this is garbage. This is garbage in terms of quantum mechanics. Remember, the save is to do expectation value. Okay, if I measure this over and over again, what will be my average value? Based on what you just saw, you're going to have h bar over 2 plus minus, so 0. Okay, so again, I hope you kind of, I know it's been a while, but don't forget, why do we do expectation values? And what happens over time? Nothing. It never changes. So, I mean, based on what you saw over here, I mean, the SZ, the plus state doesn't really change itself, right? So, anyway, so nothing's evolving in time. Okay, now, one of the things that I hope you're cluing in is that, right now, my wave function is evolving in time because I'm moving and talking, and I'm not the 0-degree crystal with 0 entropy. As soon as I've warmed up and my atoms start moving, I'm evolving in time. As soon as I pick up some entropy, I start getting dynamical, and as you warm me up all the way, I'm doing all kinds of stuff, chasing the cat. So my wave function is evolving a hell of a lot, and all the things you can measure from me, which are expectation values, are changing over time. Yet I've thrown at you just about everything I can think of, and nothing's evolving in time. Everything is a frozen crystal at 0 degrees K. And that's a really bizarre thing because the last time I checked, really nothing is a frozen crystal at 0 degrees K. Also remember, quantum mechanics says you can't ever hit absolute 0. And you should have learned that in freshman chemistry. It's technically impossible to freeze something to 0 degrees K. You can get arbitrarily close, but you can never do it. So I've shown you all these simple cases that you've learned a hell of a lot about over a very long period of time, and yet they're applicable to nothing. Remember I was saying that at the beginning of the lecture. I'm going to show you all this stuff. It's real easy. Right? This is easy. You can do this. Cool. And it doesn't, you'll never use it because it doesn't apply to anything. That sucks. Okay, so when do you actually need, quantum mechanics? So those are two cases, right? So case 3, when the state is actually a superposition Okay. When the state is actually a superposition, now remember, I said that it's just one. Yeah, it's just a ground state. But now what I'm going to do is I'm going to say that the state, the me state, the cat state, the chemical state, is ground state plus a little excited state. So that's one way to think of it. It's plus, which is aligned with the magnetic field, so that's a ground state, but I'm going to leak in a little bit of minus state. I'm going to let that coefficient be something other than a little greater than 0. A hydrogen atom in the S state plus a little p. Now it's got a little p state. What happens here? Okay. So note that based on everything we just talked about, it is now the coefficients are evolving in time. All right, so now I'm going to use this. I'm going to use this, and let's still use a non-commuting B, and let's figure out what the time that this is. And remember, we're just looking for something to evolve in time. Now again, remember, you didn't see sums in the previous stuff I did. No time, sorry. Notice how I almost wrote time evolution into the coefficient? I'm actually going to incorporate that here. So I took it back out, by the way. Or maybe I'll use it. And of course, infinity, if we're talking about its end, then it's just 1 to 2. Okay. All right, so time evolving alpha state, which is the sum of many states in the same maquette by operators. Okay, so what happens is, what's this going to do? What's this going to do? We're going to get still. Okay, I'm going to just flash my sums. It's not complex conjugate. Okay, now, I still know what the energies are, so I can still act on the Hamiltonian. I'm using this basis because it is a basis of the Hamiltonian. I'd be a fool not to do that. This is why Hamiltonian eigenfunctions of the Hamiltonian are so important, because they allow you to do time evolution. If you don't do that, you're really out of the tree. You really need to always work with eigenstates of the Hamiltonian. Okay, now let me walk you through this. Again, what is kind of sucky about this is that there's some new stuff appearing, and I want to make sure you know where it's coming from. I'm sorry. There's some new stuff appearing, and I want to make sure you know where it's coming from. Okay, so last time, remember, this was the thing that just got wiped out last time. This was just, plus a to the n minus a to the n. And that was because these states were not sums, right? These were the same state, so these were the same energies. Remember, it's a sum within a sum. So this is actually kind of hideous, right? I love the terminology, but think about it, a sum, and remember that sum is itself a sum. So it's actually kind of complicated. And we didn't have that before. So you're going to have this term here, a to the n minus a to the m. And again, because these are not always the same thing. When they are, when a to the n and that's a to the n, then it is 0 and it doesn't do anything. But because, anyway, for all the reasons I just said, there are terms that are different, ground state and silent state. Now, you might think that this thing would take care of it. If this is diagonal, then anytime m is not equal to n, it gets wiped out. In which case, this also gets wiped out because it's just e to the 0. However, and remember I already said that B is not an eigen, is not, the basis is not, B is not diagonal in this basis. Right? So that means that it's like Sx and that's plus and minus. Right? That can survive. Right? If this was Sz, plus is okay, minus is okay, but plus minus and minus and anyway, those are not okay. But if this is Sx, then plus minus and plus minus are okay. Now that means that this term will survive in a something not zero state, e to the 0 versus 1. Okay, so then what you get is that that E is oscillating with the frequency of E over H. Notice I used H instead of H bar. An angular frequency. An angular frequency would be E a to the m minus E a to the m over H bar. Remember that a frequency times 2 pi is an angular frequency. I just want to make sure that you don't get those confused. This is going to come up a lot. Right? So you notice that I took the frequency times 2 pi, that's why the H went in the H bar. So just be careful of that. Okay, so now big picture, what you got out of this is only superposition states evolve in time. So let's take hydrogen. All right, so 1s. And 3s and 3p and 3d. Okay, we showed freshmen that this is the ground state of a hydrogen atom. I'm sure there's tons of hydrogen atoms. There's lots of hydrogen atoms in space. A lot of it's in the H2 form, but there's just hydrogen atoms. What's it doing? Nothing? Like that? Huh? Moving implies then the translation operator has a time evolution.
Just hang out.
So a hydrogen atom could be doing literally nothing, right? That's true. According to what we just derived, hydrogen atoms by themselves are molecules, really. They're doing nothing. Now, here's the problem. Who believes that hydrogen atoms in outer space are literally doing nothing? Because you thought that they were what?
Moving.
They are moving, by the way. The Heisenberg uncertainty principle says you can't know how fast they're going, so they have to be moving to some extent. But then how do you resolve that with this? Right? So we've been, we've been telling freshmen that the ground state is the 1s state. Sure. But that means that hydrogen atoms in the universe are sitting perfectly still doing nothing. But nothing can sit perfectly still. And plus, I don't know, what if they find each other? They react. Well, that's dynamical. Right? But according to this, absolutely nothing can ever happen, ever. They can't even react, because that's something. So how the hell, so what is the wave function of all the hydrogen in the world? Huh? It has to have some excited state character. I 2s, 2p, whatever, just excited state. Nothing that moves or breathes or lives or moves or does anything, which is everything, is in the ground state of the Hamiltonian. Nothing. Hydrogen in the universe, the cat on my bed, me, you, we're all in excited states, to some extent. We're all admixture. But now, any of you heard quantum computing? That is a superposition state. Everything is in a superposition state, or nothing would ever move or do anything at all. So, cool, huh? That's like one of the coolest things that you will learn, that is the coolest thing